Attendees are in listen-only mode.
Right. Uh, Hello, all of us, and welcome to the webinar on PIC Architecture, Industrial Design Features. I am VP Dharmadhikari from Walchand College of Engineering, Sangli. Before we start the webinar, let me say that the webinar is of purely academic interest and does not bear any relation to the company's microchip and so on. And the whole purpose of this webinar is to introduce the viewer to PIC architecture, features, and most of the viewers being or maybe the faculty members. So I will also explain the need of such features, and if such feature is required to be explained in depth, I'll explain that also. So it is not only just list of architectural features, but it is also some explanation of why this feature is there. So the outline of this webinar will be will be getting quickly introduced to the PIC family, and then we will try to understand why do we go for a PIC architecture, and also we try to understand why people typically do not go for PIC. We will take a base microcontroller 16F877 because this is quite popular. Though there are latest versions available, we'll take up the latest versions after subsequent webinars, and some peripherals of the basic architecture. The instruction set, other tools, I'll try to list those tools, but I don't think we'll be able to go to instruction set and the understanding. So we'll get limited to the architectural features. Basically, a microcontroller is a CPU plus some peripherals plus Boolean logic and some other features like timers, serial port, and so on. So in all, it becomes a microcontroller. Why people use microcontroller? Because it's having small size. Because it leads to single chip solution. Everybody wants smart and intelligent devices. So microcontrollers are quite popular for small sizes. It leads to low cost also because everything is driven by the cost nowadays. Bit manipulation is possible in case of typically microcontrollers, but in case of PIC controllers, it's available for almost every memory bit location. And it also leads to code reduction, because if we typically write a C code like bool, suppose if we write C code bool x, then it will result in a single instruction which will result in, or if you say x is equal to 1, if you write x is equal to 1, then it will result in the instruction bit set file, and only one bit will be set, only one. It means the compilers are powerful so as to lead to a single instruction, and because of the bit manipulation, the ANDing ORing is not required, saving the code size. Then the timing problems vanish because of the microcontrollers. Timing problems vanish because if we use multiple chips, suppose this is chip 1, chip 2, chip 3, chip 4, multiple chips, and then we do interconnection, the frequency operating frequency of different ICs may be different, and a signal of this particular IC may be sometimes understood by the other IC, may not be understood by the other IC if the families are different, and so on. So it becomes difficult for multiple ICs on a single board to be used sometimes. But if we club everything together in the form of a single IC, everything is already inside and tested, so the timing problems typically will not be there. Then the reliability of the product increases because the number of solder points will be less. A lot of variety is available, especially in the PIC family, right from 8-pin package to 100 plus pins, it's available. So in the olden days, we were using 7.4 or 4.0 series or digital ICs, but nowadays we can use a small microcontroller, typically of less than 10 rupees, to replace the digital logic. The very important point regarding use of microcontroller is the code security. When we secure the code inside the microcontroller, then it will be difficult for the others to read the code, and if we are able to secure our source code, secure the program, then ultimately the designer can make money. If there is no code security, it is difficult to make money. Then as far as applications are concerned, there are lots of applications everywhere we find controllers to be used. Then we come to what is PIC. PIC stands for Peripheral Interconnect Chip, and it's produced by Microchip USA. And PIC is simply a microcontroller or a family of microcontrollers useful for industrial intelligent system design. Now, why I call it industrial system design? It will be clear when we go through the features. When we think of why we should go for PIC, then we come to know some reasons. PIC has a lot of variety, so the designer can choose from a very small IC to a large IC based on the requirement. Then the code memory, which holds the logic of the application, can be from 375 bytes, as low as 375 bytes, up to 512 kilobytes onwards. So if at all, if you have a very small logic, for example, suppose if I want to build a water level controller, then I do not need any complex logic, and since the logic is very simple, I can fit it in a small code, and if the code is small, I need not invest more money in buying a costly chip. So I can buy a small a microcontroller which has a small code memory, thereby saving the money. So you can save money wherever required, and wherever you need power, you can go to higher versions. So variety is available. So designer has choice. Many versions have EEPROMs. So why people go for PIC? Because many versions of PIC microcontrollers have EEPROM. Now EEPROM, as we know, is a non-volatile memory. Non-volatile. So this memory is quite useful. We'll take some examples to understand why EEPROMs are required typically in industrial products. Let us take an example that we have an industrial product and there is a display keyboard and so on. There is a display keyboard and there is a facility of password, adding password. Now typically passwords need to be remembered by the person who uses this, but he also needs to change the password. So if the password is changed, the password needs to be re-entered again, and it must be stored in a non-volatile manner. And if we store the code, if we store the password in RAM, then it will not be non-volatile. If we store that in ROM, it will not be changeable. So the only solution is EEPROM. So if we use EEPROM, you can change that and you can store that without any power. So therefore, we require EEPROM in some of the products. Another example of why people require EEPROM, we can take an example of say intelligent sensor, say temperature sensor. So this temperature sensor is intelligent in a manner that there is a actual sensor. The sensor is connected to microcontroller, and then it is connected to another microcontroller, which is a typically bigger microcontroller. And this sensor plus small microcontroller, which may be PIC controller, becomes intelligent sensor. Whenever we use sensors, they may be linear or they may be non-linear. So if they are non-linear, then we need to linearize them. So to linearize them, we can use linearizing function or some array or so, something like that in case of microcontroller. Now the linearity of the sensor can be different, slightly different from piece to piece, and therefore piece to piece calibration will be required, and the calibration, even if it is done, must be stored in the microcontroller, and based on the particular piece of the sensor, the table needs to be updated. So that needs EEPROM. You cannot store the table in ROM because it will not be changeable from piece to piece. Even it will not be possible to be calibrated on the site, and it cannot be in RAM because otherwise it will lose the calibration data. So you need EEPROM. So EEPROM has lots of applications, and since PIC controllers have EEPROMs on many ICs, people prefer EEPROM based PIC controllers. Then there are features suitable for industrial design. We'll see which are the suitable industrial features in subsequent slides. Then more current source sensing for port pins. Suppose we have a microcontroller, and if we want to connect an LED, typically we use a transistor to drive the LED, VCC, and if we want to avoid this, then the controller should be able to directly drive this. So, and therefore the controller must be able to sync the appropriate current. So the PIC controllers have capacity to source as well as sync more current, and therefore there is no need to connect external transistors or external drivers, and thereby saving money. There are many chip configurations options are available. We'll see why these are required and which are they. And there are some analog peripherals which are required to interface with the analog world, and they are easy to learn, and they are also easily available in market. So these are the reasons, typical reasons why people go for PIC controllers. And one more reason is that they are typically low cost also. There are also reasons why typically some people do not go for PIC controllers, because one needs to spend at least some time to do serious product development. So if you want to come out with a product, you need to get familiar with the PIC controllers, their instruction set or the related tool set, and it needs some time. If you have that much time, you can go for PIC controllers. Sometimes we need external memory support, but that support may not be present for PIC controllers, especially for small and medium range. Now that can be taken as advantage or disadvantage also, because in case of small and medium range PIC controllers, they are typically designed to be single chip, providing single chip solution. If it is so, there may not be external memory support, but for higher versions there is a memory support available. So in case you require external memory support, you can have that, but it may not be available for small chips, and it's produced only by option, so there can be issue like monopoly and so on, but that may not be issue as such. So in all, it depends on the designer. Sometimes technical specifications or technical capabilities of the IC may or may not matter, because it depends on the designer who is designing that, the tool set he has, his expertise, requirement of the product, cost of the product. So many things are necessary to be taken into consideration while designing a product, and it's not only sufficient to take the architectural features of a microcontroller. So it's better to use the suitable microcontroller for the product and start product designing. So if we feel that a particular chip has a usefulness for a particular product, it's better that we start using it somehow. So we start with the introduction to 16F877, which is a 40-pin microcontroller. Of course, it's available in other pin counts also. 16 here 16 is the series, and other series are available. 12, 14 they are smaller ICs, and 24, 32 are bigger ICs, and 16 is quite popular series. In this, F stands for flash memory. It's a reprogrammable, reloadable program memory. You can program the chip many more times, but the one-time programmable version is also available, which replaces F by C. So 16C877, it's a OTP version, and 877 is the product code. The main feature of PIC controllers is that they are based on RISC architecture. So typically they are RISC architecture. Now when we say RISC, it means reduced instruction set. It means the number of instructions are less in number. As you can see, read here, 35 instructions. So if the instructions are less in number, the instruction decoder becomes simple. Instruction decoder becomes simple. So if the decoder becomes simple, the hardware becomes simple. If the hardware becomes simple, it can occupy less die size. If it is less die size, it becomes cheaper. So ultimately, it leads to cheaper device. So it's better to go for RISC wherever we do not require large performance, and that is not the requirement of miniature intelligent applications like the intelligent sensor. So RISC CPU is quite useful for smaller products. The instructions are all single cycle, and sometimes it requires 2 cycles. The operating speed is DC to 20 megahertz. It doesn't have any minimum frequency to be operated. You can directly go up to very low frequency, and you can even drive the microcontroller by some external clock source with say very low frequency, even 1 hertz and so on. So whenever you require very low power consumption, you can drive the controller with extremely low speed. Then the code memory, that the program memory, is 8K by 14 words. Now what does it mean? It's a 8K by 14. So 8K is the size of the code memory. This is 8K, and 14 is the width of the code memory. So this is 14 bits. Usually we understand the code memory to be 8-bit wide or 16-bit wide, but here it's a 14-bit wide. Now why it's made 14-bit wide? Because if we make it 8-bit wide, then we may require 2 bytes for a particular instruction. Let's just take an example. Suppose I have an example. We'll take an example which we understand. Move imagery, you can say MBI. It's a 8051 instruction, but I take it just for example, MBI 35. So if it is MBI has 35, then 35 is loaded in accumulator or something like that. So MVI is mnemonic and 35 is the data. So you need 1 byte for mnemonic, 1 byte for data. So you need 2 bytes occupying the code memory. So you require 2 bytes. But if we have the 14-bit wide, then you can use part of this for code memory. Sorry, the actual code, opcode. I write here opcode, and part of this can be used as data. So the instructions such as MVI 35, similar to MVI A35, can be fit in a single entry in the code memory. So therefore, longer code memory width is useful, which makes the code rather denser. It means small code memory is sufficient. Then there is also data memory. But the data memory is 8-bit wide. It is written like 368 into 8. So what does it mean? It is 368 bytes, and the width is 8 bit. The width is 8 bit. The width is kept 8 bit because this is 8-bit processor, and we understand that 8-bit processor operates on a byte. So obviously the data memory must be a byte wide. So the data memory is byte wide, but the program memory is not byte wide. It is having 14-bit wide program memory or code memory. Then we go to EEPROM. EEPROM, as we know that EEPROM is useful, and there is 256 bytes of EEPROM available. We can use these 256 bytes for storing passwords, calibration data, company name, and so on. So you can store various not temporary data, but it's a kind of volatile data, changeable volatile data in EEPROM. Then pin compatibility is also there with the older versions. That's a compatibility issue. Then there are interrupt capabilities. Lots of interrupts are available. Then there is a 8-level deep hardware stack in case of PIC architecture. This is a different feature other than various other you can say architectures. So let us understand what this is and why it is useful. So we simply draw a figure 8-level deep. So what does it mean? 8 entries. So this is actually a stack. Now we do understand that stack is a place where we push and pop the information whenever the program goes to interrupts and so on. So stack is useful for push-pop operations. However, in case of many controllers, the basically stack is used for pushing as well as popping. Now, whenever we push and then pop, we are writing as well as reading, writing and then reading. So if it is writing and then reading, the stack must be RAM. It cannot be ROM. Stack must be RAM. Since it is RAM, many processors or microcontrollers use part of their data memory as RAM. Let us quickly draw it. I'll simply rub out this. Suppose this is the data memory, full data memory of a processor. This is data memory, and part of this is being used as the stack, because this is also RAM, and we require data memory is RAM, and stack is also required to be RAM. So part of the data memory is used as a stack. And whenever we start programming, the data RAM will be filled with variables, I, J, whatever variables they will be filled, and the user program will also write into data memory, read from data memory, and so on. Now, in doing this, it's possible that the variables can encroach in the stack area, or even while we do pushing, multiple pushing, the stack may encroach in the data area. It is possible because it is part of a single data memory. Sorry. So stack being the part of the data memory, stack can encroach in the data memory area, or data can encroach in the stack memory area. And if this happens, the program may crash, because the push pop things will crash. They will not work properly, and because the stack is not appropriately maintained, the program is not going to work properly. So how do we solve this problem? To solve this problem, PIC architecture provides a separate, totally separate area of RAM, which is dedicated for stack. So it's a dedicated stack. So that's why it's called as a hardware stack. Then there are only 8 entries, 8 level deep. There are only 8 entries. Now 8 entries are for only this processor, whatever we are dealing with, 16F877. For other processors, the number of entries may be less or more. There are some PIC controllers which have only 2 levels deep hardware stack. It means 2 push operations or 2 push like operations, and the stack will be full. And there are some processors which have higher number of entries in the stack. So whatever processor we are considering, microcontroller we are considering, it has 8 level deep hardware stack. So we understand that stack in case of PIC microcontroller is a totally separate RAM area, and because it's a totally separate RAM area, data memory cannot go into this, and data stack cannot go into the data memory. One more thing the architecture is doing or supporting is that there is no push and pop instruction, especially for this particular processor. There is no push, no pop. Now, if there is no push and no pop, the stack even cannot be forcibly connected, forcibly corrupted. You cannot have unnecessary pushes and pops. So stack is automatically used whenever there is a call and whenever there is a return. So if this is happening automatically, then there are no push and pop instructions, we can easily understand that the stack cannot be corrupted unless and until you have a large number of calls. Suppose if I have, I'll just rub out part of this. Suppose if I write call subroutine 1, call subroutine 2, call subroutine, sorry, not like that, call subroutine 1, and within that subroutine we have one more call, within that subroutine we have one more call, within that subroutine we have one more call, and like that. So these are nested calls, and nested calls will go on pushing the program counter. I'll just so the program counter will be pushed for the first call. In the next nested call, program counter will be pushed here, then here, like this. So if we have 8 nested calls, and if we have a 9th nested call, the stack overflow will occur and it will cause problems. So if we have lots of nested calls, it will create a problem. However, this typically may not be a problem as such, because whenever we try to write a program which have more number of nested calls, then the assembler will typically give a warning that you are using more number of calls, the nested calls, than allowed. And if we read the warning and then appropriately change the code, there shouldn't be any issue at all. So the 8-level deep hardware stack is useful because there is a separate stack, and separate stack means no corruption, no encroaching of data into the stack, and stack not growing into the data space. So this is quite useful feature from industrial point of view. Especially 8051 has a common area for data and stack, and that may cause the corruption. So this is a useful feature from industrial design point of view. As far as addressing modes are concerned, I'm going to skip those modes now, because we are not going to do any instructions. Then there is a power on reset feature. Industrial designs requires small or low cost small hardware. So this facility is that if we want reset from outside external RC, then we can use that. Suppose if I want to have RC, I can connect externally R and C. Whatever R and C we wish, we can connect. But if I want to save this, I don't want to use this, and I want to use this pin as IO, then this is also possible. It means the reset pin of the PIC controllers, which is called as master clear, master MCLR bar, active low clear. So master clear signal, which is reset signal, that pin can be saved, and that can be made to configure as IO. So you get one more IO, and the power on reset function is internally handled. So you do not have to connect external power on reset circuit, which otherwise other controllers require. So power on reset is a good feature, saving the money as well as getting extra IO. Then there is a power up timer. This is also very good feature from industry point of view. What industrial designs require is that, suppose you have a microcontroller and it is powered by the supply VCC. Now when we draw such diagram and we say that the power is connected, we assume that the VCC is instantaneously available with its full value. But if you actually see the scenario in the real circuit, you will find that the power will start from 0 voltage, because previous to switching on it was 0, and slowly it will build up to 5 volt. Now if it goes to 5 volt, then after that the operation of the processor or microcontroller will be appropriate. Before 0 there was no operation, and for the in between region the operation is not known. It means indeterminate. So we do not want industrial product to do some absurd operation, and therefore the operation of the device, operation of the industrial product must be stopped, it must not operate during this portion. The operation must be stopped. So how do we do this? There is a power up timer. It means as soon as there is a power applied, the oscillator starts, and unless the oscillator goes to appropriate number of cycles, it means, suppose we have this time axis, and then this is the time at which the power on is made. So power on is made. There is an internal oscillator which builds, and when it builds and completes typically 1000 cycles, and it gets stable, then only the processor is allowed to work. So during this period, during this actually I am explaining about oscillator startup timer also. So there is a power up timer. Whenever the power goes to sufficient high level, till that time there is an extra timer which takes care of the processor not working before the power goes to the stable level. And there is another timer, oscillator startup timer, which is for ensuring that the oscillator based on which the processor works is starting, and when it becomes stable, then only the processor or the microcontroller will start its operation. So these two features will make sure that the microcontroller will work under appropriate correct conditions only, and the microcontroller will not misbehave during the period where the power is being increased from 0 to typically 5 volts. So during this transition period, the microcontroller will not misbehave. So this is ensured by these timers. Then there is a watchdog timer. Watchdog timer, as we know, it's a timer which the watchdog timer, which we call as WDT. Whenever the program typically hangs because of some unknown reason, watchdog timer will reset the chip, and whenever the watchdog timer resets the chip, the program will restart again. So the basic concept of watchdog timer is to reset the microcontroller when the program has typically malfunction because of the unknown reason, and it's better to reset the chip rather than allowing the microcontroller to malfunction. Now the difference between my watchdog timer in other families and PIC family is that the watchdog timer is run due to on-chip RC oscillator. So this timer is run through on-chip RC oscillator. Now because there is an on-chip oscillator, it will always be running, and if we suppose we have a controller, and if we have, say, external crystal, this is a crystal, and if the watchdog timer is working on the external crystal, and if the external crystal fails, then the watchdog timer itself will fail, and if the watchdog timer fails, and the chip will not reset when the program malfunctions due to some unknown reason. So therefore, the on-chip oscillator which is driven which drives the watchdog timer makes the watchdog timer more reliable. So this is what is industrial products require, and therefore this is a good feature for the industrial design. Then there is a programmable code protection. It means part of the code memory can be made open, part of the code memory can be password protected, or full code memory also can be protected based on the need. Then there are power saving sleep modes. Many industrial products require low power consumption. So based on the requirement, the controller can be made to go to sleep. There are various power saving. There are various power modes. One is normal mode. Then the other one is idle mode. Then there is a sleep mode. There are also deep sleep modes in some controllers. In case of normal mode, it runs with almost all peripherals. In case of idle mode, the number of peripherals are reduced, and in case of sleep mode, we make the processor to go to very small power consumption, as low as, say, 1 microampere and so on. So the power consumption becomes extremely small if we allow the processor to go to sleep mode. In fact, there is an instruction called sleep. So if this instruction is executed, the processor goes to sleep mode, and thereby reducing the power consumption. Then there are selectable oscillator options. You can make the processor or controller work on either RC oscillator, low power oscillator, external oscillator of low frequency as well as high frequency. So it depends on our requirement what kind of crystal we want to use. It's not necessary that we always use a single value of crystal, as in case of 8051. You can have different crystal values based on your requirement, and based on the crystal value, if it is low, for example, if we use 32.768 kilohertz crystal, then the power consumption will be less, whereas if you use 4 megahertz or 20 megahertz crystal, the power consumption will be slightly higher, but the performance will be better. So when you require performance, you can go for higher crystal, and for when you need less power consumption, then you can go for low value of crystal. Now what is different in this is that for different crystals, the internal circuitry of oscillator needs to be slightly modified, but this automatically happens whenever you configure the chip for either working for RC oscillator, LP, XT or XA. So internally the hardware is available. You need to just configure the chip so that appropriate hardware changes will happen, and it will surely work with low, medium or high crystal frequency. So thereby appropriately giving us performance or power consumption based on our requirement. Then it's a fully static design. You can operate up to very low frequency, up to DC even. Then it provides in-circuit serial programming via 2 pins. The 2 pins typically is data and clock. So by using these 2 pins and some reset, additional reset signals, you can actually program the chip via serial programming, in-circuit serial programming. Then it is also possible to program the chip with 5-volt supply. There is no need to have a 12-volt supply for programming. There is also a high voltage mode for programming which is available, but low voltage mode is also available. So whatever is required, you can configure the chip either for high voltage mode or low voltage mode depending on the requirement. Then the same 2 pins, data and clock, can be used to program the chip, as well as you can have in-circuit debugging via those 2 pins. So this facility is there because there is on-chip debugger also in some processors. It means, for example, if you just mirror about this, and suppose this is the chip, this is the CPU, and there are some peripherals like timers and so on, and you have a program memory, data memory, and so on. Now you want to connect to this PC, computer, and then want to see what is happening inside the chip. Now to understand what's happening, you at least need to connect to this. After connecting, there should be something here. Telling you what is happening. So let us draw a person here, which we call it as a spy. So this is a spy who is sitting inside the chip and working for you. Now this spy is the hardware debugger, which is available inside the chip. So therefore, by connecting a very simple circuitry outside, this circuitry is very simple. This simple circuitry will connect to the hardware debugger, which is inside the chip, and the hardware debugger will probe into what is happening inside the chip without disturbing the CPU operation. So this is called as a non-intrusive debugger. So such non-intrusive debuggers are available in the PIC series, and which are useful. So there is no need to buy a very costly debugger and so on. So in circuit debugging via just 2 pins is available, and for that you need some hardware, and such low cost hardware is available from Microchip. Then processor read write access to program memory. Now what do we understand by this? All of us understand program memory, and suppose again I draw a processor or a controller, and controller has code memory because you need to store the program. This is the code memory, and code memory has the place for storing the code. Now the program is running, and this is basically a ROM. Typically it's a ROM. Now this ROM, whenever is stored with the program and the program is executing, the executing program, I repeat, the executing program, I again repeat, the executing program can change contents of part of this code memory itself. So this is called as the processor read-write access to the program memory itself. So it means your own program can access or change part of the code memory as a part of the program execution. Now you may say that why do we want to corrupt the program, or why do we want to modify the program? So such features are quite useful, and in fact we use them very frequently. Let me give an example of something which is not related, but you will understand what I mean to say. Suppose I have a Android phone. And I want to update the operating system. Then I can simply open some menus and say update. It gets connected, then connect to the server, then get the new code, load the new code, and restart, and it will work with the new version of the Android. Now, what is this happening? We are actually running a program, basically, and that program is available in the memory. That program is running, and it is contacting the server and updating itself. So it's actually doing something like this. A program is running, and that program is trying to modify itself. So so such kind of hardware upgradation, not hardware but firmware upgradation facility can be built into PIC controllers, because PIC controller provides read-write access to the program memory. Now this must be used very carefully because it may corrupt the program, but this is also a powerful feature, thereby allowing you to auto upgradation of the firmware. So this feature is quite useful because on the site you can upgrade the firmware of a product. So this is quite useful as far as industrial product is concerned. Now operating voltage is wide from 2 volts to 5.5 volt. Suppose if we have a battery operated instrument, obviously the battery voltage will be initially 1.5 plus 1.5 say, or maybe 4.5 for 3 cells, and it will slowly go down. And if it goes down, then typical other processes will not work, which require constant voltage, but this works at wide operating voltage, and therefore PIC controllers are useful for industrial products which are battery backed. Then we talked about high sink and source current, 25 milliampere sinking and sourcing current. Temperature ranges are available for commercial and industrial, and the power consumption is shown to be less than 1 microampere, especially at 32 kilohertz or low frequency. Then there are peripheral features like timer 0, timer 1, and timer 2. There are some timers which have prescalers. There are some timers with prescaler, postscalers also. So let us quickly understand what is prescaler and why people require that, or why PIC controllers have prescalers in that. We'll understand prescaler because timers we understand. So simply I'll say this is a timer, and we want some prescaler. Now prescaler is nothing other than one more divider. This is a prescaler. Prescaler is one more divider. So this divider will allow the timer to work at appropriate frequency, and prescalers are typically designed, I repeat this, prescalers are typically designed to be able to operate at very high frequencies, like say 20 megahertz. Even if the processor, suppose if I divide this, the microcontroller which includes the timer, if the microcontroller works at say 32 kilohertz or 1 megahertz or 4 megahertz or whatever, the prescaler can work up to 20 megahertz. It is designed in such a way that it can work at higher frequencies. Thereby, without any problem, it can divide the frequencies of 20 megahertz and 20 megahertz, and the prescaler is a programmable. Because the prescaler is programmable, this divided by n can be set through software, and because of this, you can easily use the timer. Otherwise, the basic timer will not be able to work at 20 megahertz because it is not designed that way. So prescalers are quite useful because they are designed to work at typically higher frequencies. So prescaler is quite useful. Then the timer 1 is there, but this timer 1 is able to work with external clock. Timer 1, this timer 1 can work with extra crystal. The microcontroller typically has its own crystal. Suppose this is one crystal. This is one crystal. and this is for the microcontroller, its own operation. But the timer one can have one more crystal. It can have one more crystal. So sometimes you will find that PIC controllers are connected with two crystals. One is for microcontroller's own operation, and the one is for timer one. And timer one can work with extra crystal, and it can have appropriate timing. There may be question that whenever there is a one crystal available, why to have extra crystal? The reason is that if this crystal is working at 4 megahertz, then the timer will be working very fast because the timer is running at 4 megahertz, and it will have interrupts quite frequently. And if we want to use the timer as RTC, the interrupts will be typically at 1 hertz. So there will be unnecessary interrupts, and the program will be unnecessarily going to ISRs repeatedly. Instead of that, if we connect a crystal of 32 kilohertz, if we connect a crystal of 32 kilohertz, the timer will be running at slow rate, and therefore it will have only one interrupt per second if we configure the timer as 15-bit timer. So 2 to the power 15 is 32K, and divided by 32K, 32K divided by 32K will be 1 hertz. So directly it will have once going to ISR in 1 second. So there will not be unnecessary ISRs running, and thereby not taking the CPU time. So timer 1 running with extra crystal is useful. Then timer 2 is basically a timer with a basic timer plus prescaler plus postscaler. So it will have basically 8-bit timer plus 8-bit prescaler plus 8-bit postscaler. So it becomes a 24-bit timer, and because it's a 24-bit timer, you can generate very long time delays. Then there are facilities like capture and compare. These are quite useful for industrial point of view, especially whenever we work for motor controlling. We require the timing pulses to be generated with appropriate timing. So let me rub out some of the things here. Suppose we have a microcontroller, and we want to give a square wave. We want to give a square wave, and this square wave is generated from a sine wave, which is of 50 hertz. That is mains 50 hertz, and we want to generate something out of this, which is synchronized to the input. This is the output. Now this output will be generated through software. If the output is generated through software, then there may be some timing inappropriation between input and output because it is generated through software. However, in case of some systems like power electronics devices, like say motor controller, the end-to-end timing between input and output should be perfect as per our requirement, even if there is an in-between software running. So the software cannot say that I was doing some LCD refreshing, and therefore I could not produce the output, or I was doing some keyboard scanning, therefore I could not produce the output. So such a thing is not allowed in case of high power controllers by using microcontrollers. So in such case, the capture and compare facility will be useful. We can take up the explanation of capture compare in some other session as a separate webinar if we require that. But ultimately, capture compare, this facility is useful to ensure that the end-to-end timing is perfect even if the output is generated through the software. So we have extra hardware which is called as a capture and compare. So this is useful. This is a useful feature as far as the power control is concerned. Therefore, PIC controllers are used for power control in many power control related applications. Then there are also analog to digital converter. There is a 2D converter available, 10-bit, with a very small conversion time of few microseconds, and so that different analog signals can be converted to digital, and there are multi-channel. They are multi-channel, so you can have 8 channels, 14 channels, even 40 channels, and so on. So many channels can be used to convert analog into digital. So that hardware is available. Then there are synchronous serial ports, as well as synchronous serial ports like SPI as well as I2C, which are required for interfacing with various other peripherals which are not available on chip. Suppose if you want to use the microcontroller, PIC microcontroller, and you find that the on-chip EEPROM is say 256 bytes, but you need say 2 kilobytes. So obviously you need to connect extra EEPROM. Now this extra EEPROM needs to be connected, and this connection is typically done by I2C bus or SPI bus, depending on the EEPROM. So you can either use SPI or I2C. So these engines are available inside this I2C engine, SPI engine. All these things are available. So it becomes very easy for the programmer to use them, and the program becomes typically simple. Then USART is available. There is usual COM port is available. Then there is a parallel slave port available. Now this parallel slave port is a different kind of thing, which is typically not available in other families. So let us quickly go through the parallel slave port, PSP, which is 8 bits wide with external RD, read, write, and CS. There is chip select controls available. Let us understand what this is. We are talking about PIC microcontroller, which is this, and this microcontroller is used to control various things in an application. Now imagine an application where you want to create one peripheral which is not available in market. Suppose if you want to buy 8255 and you find that 8255 is not available in market. So what to do? You have to create 8255 somehow. Now to create 8255, you need to have something which is having interface very similar to 8255, like 8-bit data bus, then read-write bus, read-write signals, and chip select signals. So if these signals are available, and if you have a microcontroller, since there is a microcontroller, you can write a program. Then there are IOs available because it's a microcontroller. So you can write a program, and the program can be written in such a way that the processor will behave very similar to 8255, and it will use IOs as port A, port B, port C, and since it is having the 8-bit data bus interface, as you can see here, 8-bit wide data bus, then read signal, write signal, and chip select signal. What this all means is that the microcontroller can be made to work as any peripheral that you can imagine. For example, the PIC controller can be configured to work as 8279. Of course, we need to write a program, and for that you can design any damn peripheral using PIC controller. So you can virtually design your own peripherals and get your job done. So if the peripherals are not available, you can do that. In fact, you can do something different. For example, suppose if I want to use a PIC controller as an intelligent ADC. Suppose I want to use this as intelligent ADC. So what I'll do is I will connect ADC channels here. Then I will use ADC. Then I'll write a program. But the interface will be very similar to 8255 interface, like 8-bit wide data bus, read signal, write signal, and chip select signal. So this will be connected to a bigger processor. This whole thing will be connected to one more processor, which can be a bigger processor, and that bigger processor will control this microcontroller as a slave controller, and this slave controller will work as an intelligent ADC. So the ADC conversion, storing, averaging, peak finding, all these things can be done. So instead of buying a costly ADC doing all these things, you can design your own intelligent ADC, and for this you need a feature which is a parallel slave port. This feature is useful in this case. Then there is a brownout detection facility in case of this microcontroller, and brownout is useful whenever the power supply goes slightly below the allowed one, because sometimes it may happen, we may expect that the output should be constant, sorry, the supply should be constant 5 volt, but if there are some dips or the supply is going slowly down, then below certain voltage the processor may malfunction. To avoid this malfunction, we are using brownout detection circuitry. So this is again a good industrial feature which ensures that the product runs without any issue as such. So I think there are also, I have covered the peripheral features. We'll quickly go through the software tools and hardware tools and then stop this session. There are software tools available such as editor, assembler, C compiler, linker. We require this: linker locator, simulator debugger, downloader, and all these things are available free in MPLAB X integrated development environment, which is free from Microchip. And there is also a code configurator which creates C code from the menu, whatever you set. So you can configure the peripherals without much hurdle. As far as hardware is concerned, you need prototype or development kit. You need some programmer. An entry-level program is PIC Kit 3, which is costing typically 3,000 rupees. So you can invest that much money and buy PIC Kit 3, and you will be able to build a small prototype on your own also. Then there are emulators, but nowadays emulators are not being used because PIC Kit 3 can do that. Debugger, on-chip debugger is sufficient for many applications, so there is no issue as such. So it's better that we go for the low-cost PIC Kit 3 version and get the job done. So these are the hardware tools. So we went through various points of introducing the microcontroller. In short, we understood why should we go for PIC, why not PIC. We went through some architecture and peripheral features, and we went through the tool sets. So I think this is the time for stopping now. Whatever is remaining, we can take up in subsequent seminars, or even the latest controllers we can take up slightly later. So I think I'm closing the session, and if you have any queries, please raise the queries. Hello? Hello?
The power up timer and oscillator startup timer are run from which power supply?
Please, sir. Please, can you repeat that?
The power up timer and oscillator startup timer are run from which power supply?
They are run from the whatever power supply we provide to the processor. For example, this is the processor, and it is connected with this power supply VCC. Typically, it's a 5 volt. So as soon as you connect the power supply, we expect the power supply to go to 5 volt. But if we expand this further, we find that it is actually like this. So it goes to 5 volt following some slope. So during this period, there should not be any behavior of the processor, and therefore there are these timers: power up timer and oscillator startup timer.
Are clock sources to pre-scaler and microcontroller different in PIC?
Clock sources for controller is typically the either crystal oscillator outside the chip. And prescaler is expected to be used for applications like frequency meter. So frequency meter, whenever we design a frequency meter, then the frequency meter code will be written in the processor, which will run. But while the code is running, it is expected to measure the frequency. For measuring the frequency, you need to give unknown frequency, and this unknown frequency is given to the prescaler input. So the prescaler is actually using unknown frequency typically. So the clock going to the processor is different, and the clock going to the prescaler is different.
What is meant by PSP, which is contained in only 40 by 44 pins?
What is meant by
PSP?
So this is actually PSP is parallel slave port. We discussed that at the end. Parallel slave port. Parallel slave port. Parallel slave port means it's a parallel port basically, and the microcontroller works as a sleeve. So this microcontroller is there, and it works as a sleeve. So if it is a slave, there must be some master. Suppose this is a master. So this master will have a master program, slave will have a slave program, and they will be communicating with parallel bus, 8-bit input-output bus, the read bar and write bar, or read-write signal and chip select signal. So these signals, signals will go from master to slave, and data will go from either from master to slave or slave to master, depending on the transaction. So PSP is going to convert the microcontroller into a slave. So you can design your own peripherals.
How is a PIC microcontroller different from 8051 microcontroller?
8051 microcontroller is not a RISC. It is not a RISC. It's having a very big instruction set. Moreover, there is a bit addressable memory in case of 8051. Bit addressable memory. Now this memory is only 16 bytes. But in case of PIC controller, all memory is bit addressable.
Can Keel software or RIDE software be used as IDE for conduction interfacing experiments on a PIC microcontroller?
You cannot use. No, Kyle. You need to use MPLAB software, which is available free and which is easy to use. If necessary, we can conduct one session on MPLAB, how to use MPLAB and how to write simple programs for PIC controllers.
Which RTOS we can run on PIC controller?
PIC has that MPLAB has its own RTOS. MPLAB supports its own RTOS. You can get this on the microchip site, and typically I haven't used any RTOS on microchip devices because RTOS requires processor to be sufficiently strong, and latest processors of PIC controllers, they are supporting RTOS. So you have RTOS on PIC controllers also, but for that you need to go to microchip site and refer to that.
Can we make DIY programmer to load the firm into chip?
Yes, you can design your own programmer which is available from web. However, the do-it-yourself programmer, they are not reliable. So you can build it, that's fine, but it is. I suggest that it's better that you spend typically 3,000 rupees to buy PIC kit, and rest assured that it works properly. So buy PIC kit 3, and that's all. If you cannot buy, obviously you have to go to do-it-yourself circuits which are available on net and do some experimentation with that. But it's definitely possible to program the PIC controller using DIY kits or circuits.
When we connect two crystals at the same time, does that work?
As we discussed earlier, we can connect one crystal for microcontroller for its own operation and 1 crystal for timer 1. So you can connect 2 crystals, but you cannot connect 2 crystals only to microcontrollers. So this is not allowed. You can have 1 crystal for controller and 1 more crystal, if at all you want, you can connect that to timer 1. And if you at all are interested in making microcontroller to work on 2 frequencies, F1 and F2, you can use the internal PLL. Now this PLL is not available in 16F877, but it is available in 18F4520 IC. So you can, I think I may have the data sheet. I can, yes, it's available here. So PLL is available. So I'll just zoom this. So here you can see that you can go from 31 kilohertz to 32 megahertz. Whatever frequency you want, you can use internal PLL, and if you use internal PLL, you can operate the processor or controller at any frequency, but at a time 1 frequency. But frequency can be changed. There is no need to use 2 crystals, but you use 1 crystal plus PLL.
Do we have Zigbee powered PIC?
Zigbee?
Yes, sir.
Zigbee, what is next?
Powered PIC.
Zigbee is a separate board as such. Zigbee is a separate board. You can have a Zigbee, Zigbee for, but you can have a PIC controller to control the Zigbee board. So you can use this as a virtual or wireless serial port as such. So there is nothing like Zigbee powered PIC as such. You can simply have a PIC small board design, and on top of that you can attach Zigbee module, and it becomes Zigbee plus PIC. PIC can have intelligence, and Zigbee can provide you communication.
And as a continuation of the previous question, they are saying, or any RF capable?
There are some microcontrollers which are RF capable. There are RF PIC ICs which can provide you radio frequency operation. For that, again, you need to go to Microchip's site and read about radio frequency PIC processors, but they are definitely available.
Thank you, sir. Even the attendees are thanking you for the session.
Okay. Right. Dhanyavad. Thanks for all the attendees for attending this session.
Thank you, sir.